So, welcome everybody. I hope you're enjoying your conference so far. It's a shame that we couldn't meet in person, but I guess that's the situation right now. My name is Michail Fartas. I'm working as senior DevOps engineer for Ignite Poland, and I've been working with Kubernetes for last 4 years, mostly in GKE, but kind of went through different releases, different types of deployments of Kubernetes, and I would like to share some of that knowledge with you. So the topic of today's presentation is going to be autoscaling versus high availability in Kubernetes. Those two uh, sell points are pretty significant in Kubernetes. That's one of the reasons why people often choose this technology, either auto scaling or high availability. But how those two interact with each other. So let's dive into that. First of all, we're gonna talk about cluster auto scaling. So how does that work? What are the benefits? How to ensure your high availability in auto-scale environment, and how this auto-scaling impacts networking, load balancing, and kind of guarantees to for deliveries. That's kind of the main point of this presentation, how cluster auto-scaling and availability interact with each other. Second point is going to be a bit on pod autoscaling. So how does horizontal pod autoscaler work, and what are the good practices for the application? Because it's not just Kubernetes itself. The application has to work within that environment. Let me move to the questions, and if there is some spare time left, we can touch on the bonus slides of presentation, types of autoscaling patterns. So to give you some background, to show you that what I'm about to share with you is coming from some of our experiences, is that first, when we started with Kubernetes, we obviously started like everyone. So it was like 3, 4 nodes cluster. But over the years, it kind of grew up to clusters that are up to 1,000 nodes. So as you can see here in this chart, this is actually a chart of number of nodes in the cluster for our production. So we have like two, for my project, we have two production clusters, and this is number of servers in the cluster. So as you can see, it changes them dramatically in the span of minutes and hours. So number of nodes changes constantly. And overall, we have seen pretty interesting cases how that type of scaling can impact the behavior in a cluster. Also, within a company, we have around 50 Kubernetes clusters, with largest one reaching up to 6,000 CPU cores and 10 terabytes of RAM. So we have different use cases, some applications that require especially focus on high availability, low latency, and other types of workloads that focus on batch processing, some background jobs, etc. And it's quite interesting how all that can mix up within this Kubernetes environment and interact with each other. So, cluster autoscaling. To bring everyone into speed, let's start with some basics, like a glossary. So, what we're going to talk about? Some basic terminology. Pod. Pod is a single instance of one or more containers in a Kubernetes environment. Basically, it's one single undividable part, and the pod is always assigned to the node for its whole life. When the pod, when it dies, it can be there can be new pods created, in a different node, but singular pod can only exist in the node that it was created on. Deployment defines how those pods are being created, what is their runtime configuration, and especially importantly, it defines number of replicas for a pod. Now, node is what we call a server in the Kubernetes cluster, and node pool is a specification of nodes in a cluster. Usually, the most important stuff about it is minimal and maximum number of nodes that can be provisioned by autoscaling. And two of the elements in Kubernetes itself are cluster autoscaler, which manages the node pool, the number of nodes based on resources, and scheduler, which assigns pods to the nodes and ensures the correct number of replicas. So how does scheduler work? Because that is crucial to understanding this autoscaling. Scheduler works usually on resources and constraints. So two basic resources that you're going to specify when you create your first Kubernetes deployment are CPU usage and memory usage. So number of cores or CPU time, and also the slice of memory, megabytes, gigabytes, pretty straightforward. But also you have constraints on the scheduling, so you can specify for the deployment like a node selector that you want to deploy on this node, or you can specify affinity, anti-affinity between different deployments. And also the node itself can have some taints, and the pods can have toleration. So basically you can specify those servers are like volatile, don't deploy important workloads here, etc., etc. So scheduler takes all that into account and tries to deploy the application onto the cluster in the most efficient way. So node defines capacity, on the other hand. You can often see in a provider, or depends on your local setup, something called allocatable memory or allocatable cores, CPU. So basically this is actually a snapshot from GCP documentation. You have different type of VMs that you can set up your cluster on. And for different type of VMs, you have different allocatable resources that can be used by scheduler. Scheduler is aware of how much resources a node can provide and judges accordingly where to assign pods. We can see that in here. So for pods, we have a definition here of limits and requests. So basically, you can define how much do you require resources for, at very least, to start operating properly, and also what is the limit for resources in order not to impact other workloads on the cluster. And down here, you can see an example deployment on a Kubernetes node. You have multiple containers, some belonging to Kubernetes system containers, and also some application containers with different requirements for CPU, for memory. And in the end, you can see how that works out in like total utilization on the node. So let's go and see how scheduler behaves in real life. So we have right now a two-node cluster, right? For the sake of this presentation, let's assume that each of those nodes has capacity of 2 pods. So let's not focus too much on the resources right now. So we decide that we want to have one replica of deployment Z, a new deployment in a cluster. So when we created this deployment, scheduler takes action, sees that there are some resources on node 2, and allocates pod Z1 onto node 2. So that's the basics. That's the first command you'll launch on Kubernetes app. But next step is scaling. So let's say we decide to scale deployment Z to 2 replicas. So that's actually usually the selling point that I talked about Kubernetes, how easily the scaling is there. So you decide you want to scale deployment Z to 2 replicas. So scheduler will notice that you have insufficient resources in the cluster. You have 2 nodes which are fully utilized right now. So what it does, it works in cooperation with cluster autoscaler, and cluster autoscaler will provision a new node in the cluster. So now, when you have enough resources, the pod is no longer like in a pending state, is now created and assigned to the node. So everything works as intended. But what happens if now we decide to remove deployment Y? So we make a request or remove from Kubernetes deployment, and the scheduler takes action and terminates the pod Y1 and Y2. And the resources are freed. So that's how basic actions in Kubernetes work. But what happens now is scheduler detects that cluster is underutilized. It knows how much resources nodes provide and how much resources it actually needs by the pod's definition. And here it clearly sees that we're not using the resources efficiently. So what will happen is scheduler will evict pod Z2. Eviction is different from termination because it comes from a different reason. So the scheduling is going to be disabled on those trees, so we ensure that no new pods are going to be assigned there. We evict existing pods on that node, and the node is scrapped. So this is how upscaling and downscaling in cluster works. So that's great. That's kind of the basic mechanism of Kubernetes. So how does this cluster autoscaling interact with high availability? So first of all, let's take a practical definition of availability. In my opinion, that's kind of combination of replication and fault tolerance. So here, let's focus on fault tolerance. The most basic one, the one that basically every operations guy is familiar with. So node failure tolerance also can be described as server failure tolerance. So we go back to our previous setup. So we just remove deployment Y, cluster downscaled, and that's our setup right now. So what happens if, for some reason, node 2 dies? Well, what will happen is if we were serving any API or interface via deployment Z, it's going to be a downtime because both replicas are down because the node died. So first step is how to prevent, how to make our application, our deployments, tolerant to node failures. Well, it's pretty simple actually. You specify anti-affinity for the pods. Affinity and anti-affinity work like, you can think of it like magnetism. You can have 2 magnets that attract each other or make them spread apart. So basically, in this case, what we want to achieve is for the same type of deployment, same type of pods to be distributed amongst different hosts. So we specify anti-affinity between the pods, which match label L1 proxy in this case, and using the topology key hosting. So we want the pods that match that label to be spread among different nodes, nodes with different host names. The same type of convention can be used to spread application between multiple failure zones in DC. And also in this case, we're using preferred during scheduling in execution, which is a soft type of requirements, different from required scheduling. It's up to you to decide whenever you want to use soft requirements or hard requirements. You can also specify weights between different affinity conditions. So with this, what we achieve is that when we move a few steps back to the situation where the cluster was downscaling, scheduler will now, when removing the pod from node 3, will not assign it to node 2. Instead, it will assign it to node 1 because it will try to honor the anti-affinity. So next step is eviction tolerance. I showed you previously about that eviction is a bit different from termination. And let's see why. Well, let's have a look at this cluster. It's similar case to what we had previously, but now instead of 3 nodes, we have 4 nodes. And also, as you can see, we have the anti-affinity nicely configured. We have replicas of pod X distributed among 2 different nodes, pod Z among 2 different nodes. So works as intended. But scheduler and cluster autoscaler now detect that, well, cluster is underutilized. So we need to downscale it. So what could happen? That's actually quite important. It's hard to predict which nodes the scheduler will try to drain, but anything can happen unless you explicitly safeguard against it. So what can happen here is that scheduler decides to evict both pod Z1 and Z2. So the effect is, again, we have a downtime, even though we had the deployment spread across multiple servers. But that's downscaling for you. So how can we safeguard against it? This is actually very easy, and often I've been surprised by how many people that use Kubernetes are not aware of its existence. It's called pod disruption budget. Basically, it's a type of policy that allows you to specify how scheduler should behave with a particular type of deployment during a downscaling or maintenance operation. This can take an effect not only during like autoscaling, which we're talking about here, but also during cluster upgrade. When the nodes are being rotated, the scheduler will take this into account. And what you can specify here is either max unavailable or min available. So you can specify that, okay, you can disable only 1 replica at a time from existing pool of replicas. Or you can specify that minimal availability is at 5 replicas or maybe 50%. You can always use percentage as well. So my recommendation is whenever you're defining your deployment, always for highly available for customer serving applications, always specify the disruption budget. And now let's move into interesting interaction between cluster autoscaling and networking within a cluster. So we're going to focus in here about deployments that are serving a service to a client, to a different application. So first, let's touch on load balancing and traffic policy. So, excuse me. Here we have an example cluster, 3 different nodes, 2 replicas of pod Z, and we have configured a service. Service is a type of Kubernetes object. You can specify service type load balancer, which will, in most of the environments, create an external load balancer, assign IP to it, that will read the traffic to your application. And how usually load balancers work in Kubernetes environments is that the load balancer will route the traffic to all the nodes in the cluster. It's not aware which one has a pod underneath. It will route the traffic to all the nodes. And only then, each of those nodes which has a port exposed for that service will get the request and use kubeproxy to route it to a specific pod. Usually, in terms of load balancing, it doesn't really matter because in the end, you have an even distribution at the end. The only thing is here is that you get an additional, sometimes you can get additional network hop, but nowadays it's not that of an issue for most of the applications. But let's take a look at one particular case. So we have a user. User makes request, goes via load balancer to node 1 to pod Z1. And let's say we have all the precautions previously mentioned deployed. So we have the affinity, we have disruption budget. So it should be fine, right? From the perspective of our pod, of our deployment Z, you have guaranteed uptime until now. You've made all the assurances that you have best availability possible. But what can happen in this case is suddenly cluster autoscaler appears for whatever reason and decides to delete node 1, which was right now routing the connection. So what will client experience is interrupted connection. As much as it doesn't really matter for short request, but if you have like long running a download of a file, or maybe a persistent TCP connection, and let's say you have many of those connections to a service in the cluster, then suddenly you will start experiencing interrupted connections, despite your best effort to ensure that the deployment is always up. So, what's the solution? One of the solutions is external traffic policy local. Basically, when you specify a load balancer type of service, you can also specify traffic policy. Default is the cluster, which I showed you before, but there is also a second one, which is called local. Basically, what it means is it routes traffic, the load balancer routes traffic directly to the node that has the pod, prevents additional network hop, and added benefit is it doesn't hide client IP, which is the case with cluster load balancing. So let's see how it works. So compared to previous setup, what we have now additionally on the nodes is each node has a health check. And this health check basically tells and with that, load balancer would only route traffic to node 2 and node 3. Additionally, the kubeproxy on that node will not route the traffic to any pod in the cluster. It will only route to a pod on that node, thanks to which we can see the client IP, as I kind of mentioned previously. So it seems right now that everything is fine, right? We have minimized the load balancing. We're not impacted by our deployment, and it's working great. Well, that's not fully it. Actually, it can be a bit more complicated because let's take a look at a bit larger scale for nodes. So we have pod Z1 and Z1 2 deployed node 1, node 2. Let's assume that Z1 is a version 1 of our deployment, right? And we have health checks working as intended. We have the local traffic policy. But now we want to deploy a second version of deployment Z. Let's say there was an update in the image, or we want to update the configuration, so we do a deployment. So thanks to pod's anti-affinity, what happens is the deployment Z2 is deployed on node 3 and node 4. It starts up, great, health check changes, and the scheduler is going to disable, kill the old version of the deployment Z1. But if you take a look at here, you'll see that load balancer is still routing traffic to old nodes. Why? Well, because load balancer has a lag for refreshing health checks, right? It's not a push notification. Load balancer has to query the health checks and update the states accordingly, right? It's still the old type of load balancer that usually would, route the traffic to classical VMs, not exactly suited maybe for Kubernetes environment, but that's what we usually have. So what we have here is basically a downtime, usually equal to health check refresh lag. So it could be like 10, 15 seconds. So what can we do about this? Well, do you remember our pod anti-affinity setup? Well, from this cute little thing, meet the big daddy. Now that's our setup. Now it looks proper, right? So what happens here? Actually, with this, we're defining both affinity and anti-affinity. So let's focus on the first part, the anti-affinity for the setup. So it's mostly the same as it was previously. So we still use topology key hostname, still use matching labels, name L1 proxy, but there is another addition. So we will define anti-affinity for the deployment L1 proxy, but we also specify for revision equals build revision. So in this case, it's like a version of a deployment. So basically what we want to do is define anti-affinity for this proxy container, but only for the same deployment version, right? For the same release. And at the same time, we define affinity. So like this magnetism I talked about, with the proxy container in a different version. So we want the containers of the same version to be as spread out as possible between different hosts, but if possible, we want them to be co-located on the nodes that had the older version deployed on. That will take effect actually only during a deployment update, but it is significant because it changes the behavior we saw before, because now the Z2 deployment is going to try to deploy on the existing nodes, on the nodes where Z1 was previously deployed. And it will also, among Z2, among its pods, it will also be trying to spread out as much as possible. And with this, basically, we're making a workaround around our health check problem, because by deploying the application onto the same nodes, the health check doesn't change, right? But obviously, as many of you probably noticed at this point, this is more of a workaround, and it's not a 100% foolproof solution, because you could be running out of resources on node 1 or 2 and what can be scheduled elsewhere, etc., etc. I have many different cases here. So let's compare those two policies and how they impact the cluster and the application. I think this discussion is quite important now, because we have seen rise more and more into multi-tenancy clusters. So you have a slice of the cluster for yourself, for your team, but other parts of the cluster are shared by different teams. You don't exactly know what is being deployed there. And people don't really think that deployments in different parts of a cluster can actually impact how your application is working. So you have sometimes take a bird's eye view on the whole cluster itself. So first, let's start with policy type cluster. Uh, Usually, it's good enough for starting point, unless you have any specific case or whatever. If you're starting, use the default. It's a default for a reason, right? And also, it's pretty good for container that is autoscaled and it's directly exposed. So basically, when your service is pointing directly to an autoscaled component, because then a kube proxy can manage on its own the connections, the routing, etc. And also when most of the cluster is working on serving that service. So if you have like even 200 nodes in the cluster, but all of them are working on serving the same service, or most of them, then cluster policy is great. Tips for that, if you're using that policy, avoid long-running connections. So you probably don't want connections that run for 10, 20, 30 minutes because you never know how it's going to be routed and you might be impacted by the connection interruption that I talked about. And also ensure that the client side that's making requests is can retry the connection and is not vulnerable to post connections interruptions, right? So it has to be like the cluster setup needs to be coordinated with both uh, application setup and the client setup. And as for policy local, in my opinion, it's good for cases where cluster is aggressively out of scale. So let's say what I showed you on the first slide, our setup, when you have like you can have additional 100 nodes in a minute and like 20 minutes later you delete that 100 nodes. For those kind of cases when the cluster is constantly changing, sometimes the local policy is better. And also it's important when you have your service serving container only a smart part of the cluster. So in many cases, I'm guessing many of you use ingress for serving a deployment. So usually when you have an ingress with ingress controller, the controller will deploy a pod of, let's say, Nginx or HA proxy within your cluster. So it's going to be a small part. So like 3 different or 4 different containers, while the cluster itself is pretty huge. So you don't want all that traffic to be put to the whole cluster. You only want it to be routed to those controllers. So another kind of aspect of the thinking of it is you never know if on different nodes there is not a deployment that is extremely highly utilizing the CPU, right? You could have a node pool that is dedicated for batch processing or for CPU heavy stuff, etc. So you could have a node servers that are utilized to the max. So you don't want those nodes to take part in routing your request queue, right? Because it will impact latency uh, and kind of the whole communication itself. And also, this is a good policy when you need the client IP on the container level. Tips for that, it's best used with some kind of controller or API gateway. Basically, when you want to minimize the number of deployment and updates here, right? So what I showed you previously. Are those 2 options the only thing we have? Well, not necessarily. There is a new how, but the problem with it is it's specific to GKE. I'm not aware of options provided by other cloud providers. But basically what GCP has done is it tried to solve that exact issue. So they leveraged their native support for pods networking and something called Alias IP, which allows direct access to the containers via IP. from other services in the same network, and basically decided that, okay, we have now ingress controller that will update those list of IPs in the load balancer. So how it works is you have something like this. You have ingress controller, or some other type of controllers in the cluster, that will look at the deployment, at the pods that are being deployed, and will update the list of container APIs into load balancer. So now load balancer can route traffic directly to pods, even skipping kube proxy, skipping like this node level. So the pods will receive the traffic directly. And although it's well, rather new setup, and I haven't actually had occasion to test it in production properly, but it has some interesting solutions like integrating with the rolling deployment to ensure that the old version of deployment is not removed until the IPs are registered in the load balancer, etc. But again, as I said, it's GKE specific, and I know not everyone is running in GKE, but that's some type of solutions that we will probably see soon in our cloud providers. So now let's talk a bit about pods autoscaling. So pods autoscaling, how does that work? Because it's actually pretty entwined with cluster autoscaling. So cluster autoscaling can be triggered by deploying of new pods, removing, adding new deployments, doing stuff manually. But number of pods can be also changed by pod autoscaler, horizontal pod autoscaler, or sometimes called HPA for short. So what it does, it periodically checks a defined metric in the cluster, and according to that metric, calculates the desired number of replicas, also respecting minimum and maximum constraints. So some setups are static, stuff like downscale, upscale, delay, and refresh interval, although as I know, were meant to be changed, I think, in release 1.18. Not exactly sure. That's also a thing to be wary about. Is horizontal pod autoscaler has multiple versions. So you'll see like version 1, v2, beta 1, v2, beta 2, and there's different availability in different clusters. Sometimes provider can restrict some of those, and keep in mind that when you're going to configure your own setup, because different versions have different specifications. So what kind of metrics can we use for this autoscaling? Well, basically we have three different types of metrics. First, the most basic one, the one that was from the first iteration of pod autoscaler, is resource based. So you can use CPU utilization, memory utilization for defining how the autoscaling is supposed to work. So we can specify, like you see in this example here, that you want to target average utilization of 70% on CPU. So it's going to specify, like, it's going to try to scale pods to achieve that all the pods are at 70% of the requested or defined CPU utilization, right? And this usually is good enough for most of like CPU-based workloads or workloads that receive like volume traffic, etc. But you might also use some more sophisticated resources. Like the first type of metric, the resource-based, is provisioned by default from Kubernetes. With the others, you have to work a bit more on configuring it. So the second one is pod-based. So how it works is each pod exposes an endpoint and kind of extracts the metrics. I'm not going to dive into that, how it's implemented. There are different methods. It's Prometheus, for example. And basically, each pod reports on its own, for example, stuff like requests per second or number of connected clients for front end serving the workloads. And you can use that, and Autoscaler can use that to achieve some kind of number between those pods to balance it out. But also you can use external type of metrics. So it could be something like pre-backlog or load balancer metrics. You can see in this example here, we're actually using integration with GCP, and we're using a metric provided by GCP, by Google PubSub, and autoscale based on number of undelivered messages in the key, and use that for getting the deployment, right? You can also specify different types of metrics, and usually how it works, it calculates all the metrics, calculate number of replicas based on each of one, and picks the max. Right now, it's not possible to have like average between different metrics. It's always going to be max. So like final good practices and tips for the application. For massively autoscaled application, obviously what's important is to have quick startup in lightweight container. Basically, when the new nodes are provisioned, you want the container to be light in order for it to be pulled quickly. And also you want to have a quick startup, because every time you upscale, you downscale, the time spent on downloading the container, starting up the container is time wasted, right? And wasted time is wasted resources, it's wasted money. It's not why we go into autoscaling. We go into autoscaling in order to use the resources as efficiently as possible. Second part is fault tolerance on the application side. The application can be downscaled, the cluster can be downscaled, so the pod can be evicted, etc. So make sure that if you're listening on a V or doing some operations in the background, that you have appropriate fault tolerance. Also, if you're making different HTTP requests, always remember about retries, etc. And obviously, make your application as stateless as possible. That should be no-brainer by now. If you have doubts, follow the cloud native guidelines. It's really actually important and can save you a lot of time. For infrastructure, once you achieve these previous steps, like your application is tolerant and easy scaled and not impacted by the node failure, etc., you can start utilizing stuff like cheap or unstable VMs. In GCE, for example, you have something called preemptible VMs. It's a VM that has maximum life of 24 hours, but that's only maximum. It can be deleted or kind of reobtained by Google at any point in time within those 24 hours. So they can die wherever without much of the worrying. But the addition is they're 80% cheaper than standard VMs. So if you can make your application, tolerant to those node failures, let's call it preemption, then you can reduce the cost significantly. And also something that's not often talked about when considering autoscaling is, people often think about the obvious bottlenecks, such as databases, such as cache, etc. But what people often forget is that large scale also impacts other components, such as monitoring, logging, image registry, and DNS. Those are stuff that often surprise people when, for example, they decide, okay, so let's scale this application to 500 nodes in the instance, let's provision it, etc. And suddenly, some containers are not starting because the registry is actually not being able to keep up with delivering those images. Also, kubedns, those issues, those can be a bit difficult to debug, but my recommendation is when you have a large enough cluster with different type of node pools, take a look at your kubedns, the configuration, make sure it's resilient as it should be, because sometimes it can play different tricks. And also, final tip, watch out for silent failures. at scale, when you have thousands of containers are being reprovisioned, etc., it can be easy to miss the stuff that failures that come out of container running for a longer period of time, or in a huge heap of containers, one or two restarts may seem unimportant, but can actually indicate some more serious problems. So thank you very much for this first part of this presentation. Well, if you want to download it, here is a download link for the presentations. You can always also contact me on LinkedIn if you want to discuss some issues about Kubernetes in the future. And also, I encourage you to follow Ignite Poland on Facebook, LinkedIn. So let's now see what questions do we have. So, what would be a proper load balancer setup when hosting Kubernetes cluster on-premise on physical machines? Well, honestly, as usual with those type of questions, the answer is usually it depends. Basically, it's hard for me to say what is your exact setup. What are you using for controllers for the balancer? What technology of load balancing are you using? Is it just a controller, or is it how are you deploying it? Basically, what Kubernetes usually offer is exposing a service on the nodes as a node port. So basically, port on each node is going to be for delivering this service. And it's up to you or to a provider to specify how the traffic is routed to those nodes. So basically, for providers, cloud providers, GCP, it's going to be a network load balancer or HTTP load balancer provision for that. And in your own case, honestly, I cannot say. It depends on your initial setup on-premise. Network load balancing for AWS AKS. What is the best practice to use NJX or ALB or both? So I haven't much experience with load balancing and Amazon, so I cannot say much about ALB. I can say that I had some experience with GLB and Google, so Google Load Balancer. So basically, if we compare setup where you have an ingress controller within a cluster and simple network load balancer to route the traffic versus having more sophisticated load balancer by provider on a higher level HTTP load balancer by provider, and then a dumber only service, your controller that only configures that service by the load balancer externally. I would say use the basic load balancer. I think, in my opinion, personally, try to route the traffic to the cluster with the lower layer protocol. So you want to use TCP load balancer, for example, to route the traffic to the cluster itself. I had some difficulties, let's say, with more sophisticated ingress controllers. Sometimes you find out that provider does not support this operation or that operation, and well, as long as you're following default, it's fine. But when you have more sophisticated, it can be a pain. So I would say like use lower layer load balancers for zone traffic. What's next? Can you share some tips for kubedns at large scale? Okay, so first tip right out of the box is go into your cluster and check the config map, which is called kubedns autoscaler, I believe. Basically, kubedns is has a bit different setup. It has autoscaling, but it's not like horizontal code autoscaler. It has this additional deployment that is doing autoscaling based on a metric which is called nodes per replica. So basically, kubedns is scaled when the cluster itself is scaled. So for that, if you happen to see some issues with DNS, you might want to modify that config map and basically specify higher number of replicas per or like per nodes per replica, like lower nodes per replica count. So you have more instances of DNS. It is also specified somewhere in Kubernetes documentation, but it's kind of in some more hidden sections. Also, something you might take a look at is if you're running stuff like preemptible VMs or VMs that are under heavy workload, etc., you may want to edit the existing kubedns configuration in order to prevent kubedns being deployed on those type of nodes. Because if like kubedns instances are being evicted, etc., it will be visible in the application. You're gonna have DNS issues. Does pod ready plus solve some of networking issues you've shown? Yes, it does. It is actually this ready plus, which is now called, I think, readiness gates. It is being used by the container native load balancing. So what I showed you previously, where a controller updates the load balancer with the list of the IPs of new pods, that is actually using readiness gates. So pods are considered fully ready, but deployment only after they've been registered into load balancer. But honestly, I'm not sure about has that been implemented into other like ingress controllers, etc. I'm not sure about that yet. And also kind of you should keep watch. You mentioned that it was introduced in 1.14. Make sure that it's enabled for your provider, because sometimes features are introduced with like many Kubernetes release, but they're not available for your deployment for your provider. Okay, I think that's all the questions right now. And unfortunately, we're out of time. So thank you guys very much. You can download here this presentation, and also you have some additional slides you can read about different types of autoscaling profiles and what metrics could you use for your application for different type of scaling profiles. Thank you very much, and enjoy the rest of the conference. Thank you.